Okay, so here is what we're going to do on this one. It's to simplify the square root. So clearly we're not looking for plug it into the calculator and then be done, because that wouldn't even require a topic. So instead, what we're looking for is a way to simplify this. So, I mean, I could rewrite this with multiplication as 2 times 14, and that would be true, yeah, because 2 times 14 is 28. Or I could write it as 4 times 7, and that would be true because 4 times 7 is 28. However, this is the one that is going to work better because it has something I know how to break down. It has a perfect square. I know that the square root of 4 is 2, and so I can write it like that. And that's the final answer. 2 times the square root of 7, 2 root 7. As always, if I want to, I can check my work. Always a good idea. So the square root of 28, is that actually the same as 2 times the square root of 7? Yes, they match up. So I know I did it correctly. And I think we should try another one because they're just so darn fun. Okay, so on this one, is there a perfect square that divides into 80? Yeah, 4 does, but so 4 times 20, and the square root of 4 is 2. But you know what? There's a perfect square that divides into 20, and that's 4. So the square root of 4 is 2, again, and we get 4 times the square root of 5. Now, we could have done it a little faster if we had seen that, you know what, 16 divides into 80 5 times. And the square root of 16 is 4. And I'm done. If you do it the fast way or the slow way, it doesn't matter. But you do have to go as far as you can. Pull everything out that you can. Now we do that again, but with variables. So is there a perfect square that divides into 12? Why, yes, 4 divides in. I know the square root of 4. Okay. And we've already learned in, oh yeah, so I'll go down. So the square root of 4 is 2. And we've already learned how to handle the square root of w to the 16th. That's w to the 8th. And so that's handled, that's handled. The only thing left is the 3. So square root of 3 stays in there. That's it. As always, I can plug that in for y1, plug that in for y2, go to the table, see if they match. Now let's do one with an odd exponent on the variable. First, are there any perfect squares that divide into 48? 4 does, but so does 16. 16 times 3. Now, for that v to the 17th, v to the 17th is, I could write it as v to the 8th times v to the 8th, that's 16 of them right there, times 1 more v. And then I can say, well, hey, I know that's 4, and there's a pair of v to the 8ths. So I get, there are 2 v to the 8ths in there, so I've got one group of v to the 8ths. And then there's this guy left over. And every time you've got an odd exponent there on a square root, yeah, you're going to have a variable left over. So what I did to break it down like this is I said, hey, v to the 17th, let's, just do v to the 1st, like that. And then that v to the 16th, let's chop it in half. And then that's, kind of how I know where to go and what to do with this one. Now we do the same thing again, except this time I am going to use red. Oh, and there's a second variable in there. Big deal. Okay, so square root of 16 is 4, and I've got 5 y's. Okay, so I've got 2 sets of y's with 1 y left over. Okay, and I've got 4 sets of z's with 1 z left over, and that's the whole thing. Okay, because y to the 5th can be written as, whoops, that's equal, as y times y squared. And so that gives me the y squared. Z to the 9th can be written as a single z, and then I've got z to the 4th, and that's 9 z's. And then boom, I got 1 set of z to the 4ths. And so that's how I got there. Now let's get back to no variables, but not square root, but some other root. So to do this, to simplify it, without a calculator, although you can check it on your calculator, and you should, it would be super cool to factor this. So 54 I know is 2 times 27. I know 2 goes in because it's even. And 27 is 3 times 9, and 9 is 3 times 3. So I've got 3 3's and a 2. So 2 times 3 Q. Let's see if I can draw that. That's a 3. All right. Now we are looking for groups of size 3. So I don't have enough 2's to pull anything out. So the 2 is going to stay inside. But there is, I got enough 3's there that I can pull something out. I got 1 complete set of 3's. And the 2 stays inside. And you'll notice I was careful to write this out so it didn't look like this 3 and this 3 are together, like it's the 33rd root of 2, or it's 33 times the square root of 2. Let's check that on the calculator, shall we? So I'm going to go clear. Let's clear this off too. All right, so I'll go math 4 for cube root, and then 54. All right, so I get that. Cool. And then 3, and I have to hit the times sign before I do the 3 for the cube root. If I don't, then it looks like the calculator says 33rd root. Okay, math 5. I know I did cube root 2 different ways, whatever. And I get the same answer, so I know I'm good. I haven't made any mistakes. Alrighty, so now we've kind of put it all together, and so we're looking for groups of size 4. Okay, well, 48, I know from all the things we've done in this video, 48 is 3 times 16, and 16 is 2 to the 4th. And then, so, hey, there's 1 set of 4 items. Well, I could do y to the 16th, I could write that as y to the 4th, y to the 4th, y to the 4th, y to the 4th. Okay. And then z to the 17th, I could write that as z. You know what, this time I'm just going to say z to the 4th to the 4th power. I could have done that with those y's, but I didn't bother. Okay, so I've got 1 complete set of 2's. Cool, so that's outside of the radical. I can't pull any 3's out. I've only got 1 of them. I need 4 to pull them out. I have, here's a set of 4 items. Okay, I've got 4 of these y to the 4th creatures, so I can pull out a y to the 4th, or I can pull out a y, then a y, then a y, then a y, and still get the same thing. All right. By the same token, I've got 4 z to the 4ths. Oh, okay. So that's a complete set of z to the 4ths. So that can come out. And then what's left over? The 3 and the z. The z. Hang on, something important just happened.